Hey guys, so in this video, we're going to do a review of translations and reflections of functions. So this is kind of like the second video in a series. So I had another video where I talked about some basic graphs. So I'm going to explain this technique, but if you feel like you're struggling with it, I would recommend just checking out my video on basic graphs. It'll give you some other tips to help you with this if you're struggling with this. Also, this is considered to be a review video, so it's kind of intended for like pre-calc and above. If you are looking for a slower paced video on this topic, I have those. I'll drop some links in the description. Okay, so the first thing that I want to review is what is a vertical translation? How does it work? So what we're going to do is we're going to take a virtual field trip to Desmos.com. Okay, so let's go. Now, if you're trying to learn this, I would actually write down or make a little sketch for yourself just so that you can kind of retain this better. So, okay, here's how the vertical translation works, the best way to understand this. This dotted line here is going to represent the absolute value of x. So that's that graph. So now what I want to see is what happens if I add 2 to that. So, boom. I've added 2. It's the red function here. So notice, let's see, I'll scroll in a little bit. So you can see that this graph has moved up 1, 2 units. So it's still the shape of the absolute value of x. It's just been moved up, so it's been translated. And then what about if I subtract 4 from that? Huzzah. Okay, so now I've moved down 1, 2, 3, 4. So you can see now how this really works is if you add or subtract a number just from the outside of the function, this always works. Now, I showed you this with absolute value of x, but you can do this with any graph. So this is just a thing that works all the time. So let me just change these. Okay, so now I've just changed, and you don't have to copy this down, but just to show you that this always works. So here's my function square root of x. So if now I change this to square root of x plus 2, so look what happens. It moved up, right? So it moved up once again by 1, 2 units. And if I were to subtract 4, now you can see that this graph has just moved down. So it stays intact, it just changes. And then, just to really drive the point home, it really doesn't matter what graph you're talking about. So if I have now, say x cubed is my base function. So look what happens. If I add 2, it moves up 2, right? You can see it boom, boom, moving up 2. And if I subtract 4 like I do here, again, you can just see that. So this is what translations are supposed to do when we discuss these. So this, when we talk about how it moves one graph, I want you to think about how it applies to all graphs like you see here. So what makes a vertical translation then is you have the function f of x wherever you're starting and you add a number to it, and that represents the idea of the vertical translation. So you're moving it up or down. And if you have a plus k, that moves the function up. If you have a minus k, that moves the function down. So that's a vertical translation. Okay, so next let's talk about horizontal translations. So once again, we're going to go back to Desmos. So now if you're playing along at home and you're taring to sketch this out, so I'm going to start with x squared as a base graph. So to do a horizontal translation, so notice how this is different from what we were just talking about. So now I have x plus 4, but that whole thing is squared. So with vertical translations, you would have the plus 4 on the outside of the function, and I always think of this now as a horizontal translation. You're doing something directly to x inside of the function. So hopefully that kind of makes sense. So let's see what happens when I add 4. So when I add 4, so what's interesting is that this actually moves in the opposite direction. Maybe you thought it was going to move to the right 4, but it actually moves in the opposite direction. So notice now this is at minus 4 where this starts. And so then by process of elimination, if I were to subtract 2, so now to do this other horizontal translation, so now check it out. This moved my graph of x squared 2 to the right. And so this works just like I showed you with vertical translation, so it also works with any function with a horizontal translation. So that's the idea of the horizontal translation. And the way that we talk about this is f of x minus h. So notice now this is happening within, next to that x within the function. So f of x minus h represents a horizontal translation of the graph of f of x. So when you have minus h here, that's going to move h units left, and then when you have plus h. This is a plus h, not a th. When you have plus h, this moves h units right, okay? So that's the idea behind a horizontal translation. Now let's talk about reflections. Okay, so for my base function this time, I'm going to use the square root of x. So for the first reflection, I've got the negative outside of the function like you see here. So let's see what happens. So by putting this negative on the outside, I've flipped over the x-axis. So it's the exact same graph. It's just literally flipped right over that x-axis, okay? And then what about if I were to not have the negative on the outside of the function, but instead, let's say, next to the x inside of the function? What do you think is going to happen now? Now we flip, it's the same function, it's just now flipped over the y-axis. So this is how reflections work. So to summarize, reflections over the x-axis require that we take a negative on the outside of that function, and that will give us a reflection over the x-axis. Meanwhile, if I have a negative within the function next to my x, that will represent a reflection over the y-axis like we saw previously. And the last thing I want to talk to you about now is the idea of stretching and shrinking. Okay, so for stretching and shrinking, I think this can be a little hard to wrap your head around. So let's start with the base function, absolute value of x. And then let's take a look at what happens when I multiply that by 2. So what's happening here is, so the function looks narrower, and I want to point out just like a key point here. So on the original function, we have the point, let's see if I can get it to come up, 1, 1, right? You see that, 1, 1. Okay, now if I come up to this function, notice this is the point 1, 2. So what that 2 is doing is it's like raising up where the y coordinates go, and that's why it has kind of this like pulled up narrower shape. Versus if I have 1/2 times the absolute value of x, so now look what happens. So it looks like it's wider, maybe it's been stretched out a little bit, however you want it. Like I feel like the words stretching and shrinking are not totally precise, but it makes the graph look wider. And so I just want to point out, so remember this was the point 1, 1 here. So this point here is 1.5, 1 and 0.5. So that 1/2 now is, again, it's kind of like impacting that y coordinate. Now, what gets tricky about this is you can also do, so I'll show you. So I could also do something like the absolute value of 2x. And in this particular case, like by changing the graph to the absolute value of 2x, it doesn't change the graph at all. So this is kind of like one of the harder things to kind of figure out is what happens now if you multiply on the outside of the function versus the inside of the function. Sometimes nothing happens, sometimes something does happen. So I'm going to show you the details kind of with what makes stretching and shrinking. But the reality is I don't think you have to remember which one is stretching or shrinking or what. I'm going to instead show you kind of like how you can figure out what a number like this is doing to the graph. And the bigger thing to kind of remember is it still looks like the absolute value of x. It still looks like its base graph. It's just going to have this stretch or shrink factor. So it doesn't create like some totally different shape, right? It's still what the graph is. So let's just take a look at the technical definitions. Okay, so these are the technical definitions. I think these get a little tough, and like I said, I will show you kind of how to figure out what's really happening once we get into the graphing. But a vertical stretch happens if you have a times the function, so kind of you're multiplying a kind of on that outside part of the function. And from a technical standpoint, there's stretching if that a is greater than 1, and there's a shrinking if a is between 0 and 1. And then we could say that there's a horizontal stretching or shrinking, and that would happen when a is multiplied directly against x. So it's a horizontal stretching when a is greater than 1, and a horizontal shrinking when a is between 0 and 1. But again, I think this gets very technical, and I think this is one of the harder ones to get intuition on. So we'll play with the graph so that you can really get some intuition. So what we're going to do now is we're going to describe what happens to these graphs f of x. So what is happening to them, and then we're going to graph them, and we're going to show you how you can like quickly graph these different functions. All right, so I've got f of x equals negative x squared plus 3. And so what I want to do is I first want to just describe what is happening. We've got the graph of x squared, and so you should know what that graph looks like if you watched my other video. And so what's happening to that graph is I've got the negative out here. So it's being, let's see, I'll label this. Oops, let me grab a different color. Okay, so this is being reflected over the x-axis, right? And then what does this mean? This means that it moves up 3. That's what's happening here. Okay, so I just want to remind you real quick. So the general graph of x squared looks like this. So I think of 3 main points. I start here at 0, 0, and then I have these 2 other points. I go out 1 and up 1 in each direction, and I have this U shape. This is what I think of when I think of graphing x squared. So what I'm going to do is I'm going to take, I think of the vertex, this is kind of like my starting point. I'm going to move that up 3, 1, 2, 3, and I'm going to start there. Now, to flip this, so just think about the mechanics of plotting those 3 points. Normally, I go out 1 in each direction and up 1 in each direction, but now I need to flip this. So instead I go out 1 in each direction and I go down 1 in each direction. So out 1, down, and down. Okay, and so now look, I have this ready to open in that downwards position so that it can be reflected. So it's going to look like this. Now it doesn't reflect perfectly over the x-axis because it was moved up 3, but you get the idea. Okay, so that's the way that we want to think about these problems. So let's take a look at another one. So now I've got g of x equals x plus 2 cubed minus 3. So just thinking about what happens here. So this plus 2, it happens on the, I always think of this as the inside of the function. So this means that we move, so it moves, let's see, it moves 2 to the left, right? And then this means it moves 3 down. And I need my graphing axes. Okay, so before I draw this, once again, I just want to think about what is the deal with x cubed? How do I graph that? So I talked about in my other video, so I have these like 3 main points, and then it has like this curvy shape to it, right? So what I want to do now is I want to take that central point of 0 and I want to move it 2 left and 3 down. So I'm going to move 2 left and 3 down. So here's my starting point. Now everything else about how I'm going to graph this is going to work the same. So I think about this behavior of I've got the center point drawn, and then I go out 1 and up 1 in one direction and out 1 and down 1 in the other. So if you just think about like how these 3 points relate to one another, you can copy and mimic that behavior on your translation. So I'm going to go out 1 and up 1 here, out 1 and down 1 here. I think about how those relate, and then I draw the exact same shape. Okay, so for C here, so now I'm just throwing the kitchen sink at you really. And okay, so I'm going to also show you like how do we think through these other stretching and shrinking factors. All right. So this negative sign means that we're going to reflect over the x-axis, right? This plus 1, which way am I going to move, left or right? So we're going to move 1 left. The minus 5 means I move 5 down, and then we have this 2. Now this 2 is technically being multiplied on the outside of the function. There's a couple different ways that you can handle this, but I'll kind of tell you the easiest. So first of all, if I think about the graph of x squared, okay, so think about what this looks like again. So the normal graph of x squared starts here, I go out 1 in each direction, I've got my U shape, bada bing, bada boom. All right, now what this 2 is going to do is it's going to take these y coordinates and it's going to move them by a factor of this. So basically I can take these 1's here, so this occurs at 1, right? So 1 times 2 is just 2, right? So what's going to end up happening is now instead of going out 1 and up 1 in each direction, I'm going to go out 1 and up 2 in each direction. This is what's going to happen to it. So you want to think about how this number is going to pull the other two kind of anchoring points in your function. We'll do this again. I know that was kind of a lot, so let's graph it for now, and then let's try it like one more time so that you can get some more practice. Okay. So anyways, so I need to start with my 0, 0 point, and I need to move it. So I'm going to go 1 left, 5 down. 1 left, 1, 2, 3, 4, 5 down. Cool. Now, I know that instead of my points going in the upward direction, they need to go in the downward direction. And then I also know I'm going to go out 1 in each direction. And now instead of going down 1 in each direction, so that I can get that stretch factor, I'm going to go down 2 in each direction. And so it's still a parabola, but now I've got that stretch factor in it. Okay, so let's try that one more time with another stretch factor and another crazy reflection. Okay, so in this case, I've got a minus sign here. Since it's inside the function, that means that we're going to reflect over the y-axis, right? This plus 1 means we're going to move up 1. And then this 2, again, is that stretch factor. So we have to think about how is that going to impact the graph. So if you think about this in terms of, here's my normal square root of x. I start here at 0. I have this other point 1. This is normally what it looks like. So now I want to take this y coordinate and I want to multiply it by 2. So that's going to move the first point, instead of it being out 1 and up 1, that's going to be out 1 and up 2. And so here's how that stretch factor is going to impact it. So that's the like how I want to think about how to mess with the y coordinate. So now I have to translate all of that thought right to this. So there's a lot of things to think about. So we need to reflect over the y-axis, and we also need to move up 1. So the first thing is I'm going to take this anchoring point, this 0, 0, and move it up 1. Oops, and I'm having problems with my mouse. Okay, or my pen. Okay, so I moved it up 1. Now, since I'm reflecting over the y-axis, normally my graph goes this way, right? But since it's being reflected over the y-axis, I need it to go this way. And so I'm going to go this direction, and then how far am I going to go? I'm going to go up 1, 2. And so here is that graph. Now, I think this can be like one of the things that can be a little harder for some people. So if you are struggling with this and you want to watch more examples, like if you feel like you kind of got it, but you could use more review, don't worry. I have a lot of different ways you can get more review on this. So just look in the description of this video and I'll drop a bunch of different links so that you can get whatever level of extra instruction you want on this if you feel like that wasn't enough review. The last thing that I want to do in this video is I want to write the equation with the given characteristics. So what we're going to do now is we're just going to go the opposite way. So I want a function, I want x squared moved 3 units left and 5 units down. So how would that look? Well, that would become f of x equals, so to move left, I'm going to add 3. And then to move down, I'm going to subtract 5. So that's what we're looking for, is just how would you actually write that function. So I've got one more here. So the function cube root of x reflected over the y-axis, that's important, translated 2.5 units right and 1.75 units up. So maybe you want to pause here for a second, think about that, and then hit play when you're ready. Okay, so in how this is stated, I'm going to want to have negative x here, and then translating 2.5 units right. So I need to subtract 2.5 within the function, and then move up 1.75. So that would be my function. Okay, and so that brings us to the end of this review video. So like I said, if you feel like you need more, this is kind of meant to be like a quicker review for pre-calc students or like calc students who are maybe just a little rusty on this. But sometimes this isn't enough review, and sometimes you just got to go back and kind of refresh the whole thing. So I'll drop links to all of that. Don't worry, I've got your back. I just have to keep this video shorter, just, because it is supposed to be a review. Okay, so I will talk to you guys in another video. Thanks for watching.